And welcome to Technology Tap. I'm Professor J. Rod. In this episode, from watts to cores, building a stable PC. Let's get into it. Welcome back to Technology Tap, the show where we bridge theory and real-world technology. I'm your host, Professor J. Rod, and today we're building from the ground up the power, storage, and memory in CPU to form the backbone of every stable system. By the end of this master class, you'll understand how to choose efficient PSUs, configure RAID arrays for both performance and protection, tune memory for bandwidth and reliability, and select CPUs that keep pace with modern workloads. This episode is your roadmap to build smarter, troubleshooting faster, and passing that CompTIA A+ exam with confidence. Let's get started. Every stable build begins with power. It's the one component most new technicians overlook, yet it dictates everything: performance, longevity, and safety. Start by adding your system's total wattage, CPU, GPU, drives, fans, then add 25 to 30% headroom. This overhead ensures your PSU can handle transit spikes, those certain surges in current, when GPUs boost or CPUs ramp up under heavy loads. If your rig pulls 500 watts under stress, aim for at least 650. It's better to have extra capacity than risk instability. Now check efficiency. The 80% certification program measures how much power converts into usable DC power, and it's into 4 different categories. Bronze is 82 to 85%, budget-friendly, hotter, noisier. Silver is 85 to 88%, mid-range builds. Gold is 87 to 90%, ideal for most users, efficient, quiet, cool. And platinum, titanium is 90% plus, premium servers or continuous workloads. Higher efficiency means less waste, heat, lower noise, and reduced energy costs. Next, consider ATX 3.0, the new PSU standard. It introduced the 12VH PWR connector, a single 16-pin cable delivering up to 600 watts for next generation GPUs like NVIDIA's RTX 4000 series. It replaces multiple 8-pin connectors and better manages transistance loads. Warning, avoid bending the 12-volt HPWR cable sharply near the connector. Keep at least 35 millimeter clearance to prevent overhead. Choose your cable design wisely. Fully modular, every cable detached, best for airflow and cable management. Semi-modular, fixed core cables and detachable peripherals. Non-modular, all cables fixed, cheaper but cluttered. Now, protect that power. Pair your PSUs with a UPS, uninterruptible power source, to guard against blackouts and add a surge protector for voltage spikes. A UPS gives you time to save work and shut down safely and gracefully. Essential for office and lab environments. Keep your system power states too. Sleep, RAM powered, quick resume, hibernate, RAM save to disk, zero power to use. Hibernate sleep combines both safe during power loss. Choose sleep for short breaks, hibernate for longer downtime. Finally, cooling. Heat is the enemy of electronics. Follow this airflow rule. Front bottom intake, rear top exhaust. Apply thermal paste sparingly. A pea-sized dot in the center spreads evenly under pressure. Don't put it like if you're making a sandwich and you're putting mayonnaise on it. That's not how it works. Let's not do that, guys. Liquid cooling handles heavy loads quietly, but check for pumps and fittings regularly because it might leak. Story time. A student once paired a 4090 GPU with a 500-watt bronze PSU. Random reboots plagued every gaming session. After upgrading to a 750-watt gold ATX 3.0, stability was instant. Remember, power isn't where you cut corners, it's where you invest in reliability. Storage devices and RAID. Let's store some data. Storage determines not only capacity, but also speed, safety, and system behavior. 3 main storage types: HDD, spinning platters, slower, cost-efficient. SSD, flash-based, silent, faster, shock-resistant. NVMe, PCIe interface, extreme speed for OS and active files. But drives are only half the story. How you organize defines performance and redundancy. That's where RAID, redundant array of independent disks, comes in. Let's explore each RAID level, its mechanisms, advantages, and disadvantages. RAID 0, stripping. How does it work? Data splits across 2 or more drives for parallel read-writes. What does that do? What's the advantage? Maximum performance. Ideal for large sequential read-writes, 100% capacity utilization. Essentially, you're using 2 drives that act like one, so that each one takes turn reading and writing. So it performs really fast. Disadvantage: no redundancy. If one drive fails, all data is lost. Rebuild impossible. Backup mandatory. Best for scratch disk or temporary rendering spaces for non-critical data. RAID 1, mirroring. How it works: data duplicating on 2 drives. What's the advantage? High fault tolerance. Survive 1 drive failure. Easy recovery. Just replace the failed drive and rebuild. Disadvantage: 50% capacity efficiency, 1 drive's worth of storage, slightly slower writes. Best for OS drives, small business servers, mission critical boot volumes. The one thing about mirroring is you're paying for 2 drives, but you're only ever going to use 1. So you have 4 2-terabyte drives, you had 8 terabytes of space, you're only always going to use 4. That's the bad thing about mirroring. But the good thing is you have a backup. You always have a backup. RAID 5, stripping with single parity. How it works: stripes data and parity across 3 drives. What's the advantage? Balances performance, redundancy, and capacity. Survives 1 drive failure, efficient use of space. What's the disadvantage? Slower writes. Parity is calculation, so it's slower. Long rebuilds, increased risk of a second failure, which you have another drive that fails, you're going to have total loss. Best for file servers, media archives, environments, balancing speed and safety. Now, in the CompTIA books, in the instructions, in the data, and all the stuff that you find from CompTIA, they will tell you that if your RAID dies, wait until it's downtime to replace it. In my experience, I replace it right away, because if you have RAID 5, because one drive already died, who knows when the other one might die? So you change it right away. You don't, if it dies on Tuesday, you don't wait till Saturday to change it, right? You want to change it now. So, and the literature tells you, wait. You don't really want to wait. All right, RAID 6, stripping plus dual parity. Here's how it works: 2 parity blocks stored across 4 or more drives. The advantage here is 2 drives can fail, right? Safer during rebuild. The disadvantage is slower writes due to dual parity, reduces usable capacity. Best for mission critical storage, large arrays, enterprise NAS, or network attached storage. RAID 10, stripe mirrors, 1+0. How it works: mirrors pairs of drives and then strips those pairs. Advantages: it combines the speed of a RAID 0 with a redundancy of RAID 1. Fast rebuild, only mirrored ones are affected. Excellent performance and fault tolerance. Disadvantage: again, you have 4 drives, you're only really using 2, right? 50% capacity, higher cost, double drives. Best for database, virtualization, heavy I/O workloads. The key reminder with RAIDs protect against hardware failure, not human error. Deleting a file, RAID won't save you. Always maintain external or cloud backup. Story time. A design firm trusted RAID 5 alone. One drive failed, then another during the rebuild. 10 years of work gone. They switched to RAID 6 plus nightly cloud backup. Protect data twice, redundancy and backup. Segment 3, memory mastery. Memory is your system's workplace. Fast, temporary storage for active data. The CPU fetches from RAM thousands of times faster than disk. RAM generations, DDR3, 1.5 volts, up to 2,133 megahertz. That's a legacy system. We don't usually do DDR3 anymore. DDR4, 1.2 volt, up to 3,600 megahertz, mainstream standard. And DDR5, 1.1 volt, 4,800 to 8,400 megahertz, dual 32-bit subchannels on DIMM PMIC. Each has unique notches. You cannot put a DDR3 into the DDR5 slot or vice versa. It will not work because they won't fit. Performance depends on frequency and latency. Higher megahertz equals more bandwidth. Lower CLs is a faster first access. True performance, latency divided by frequency times 2,000. The lower the number, the better. Channels multiply throughput. Single channel 64-bit is baseline. Dual is 128-bit dual bandwidth, and quad 256-bit servers and workstations. Use match pairs in color-coded slots. Mismatch modules drop to single channel or flex mode, reducing speed. So you might have 4 slots and they're color-coded red, black, red, black. You put one in the red, the other one has to go in the red if you only have 2. If you only have 2 RAM chips. Now, if you have 2 4 and 2 8 gig, you put one 8 gig in the red, the other one has to go in the red, and the other 2 go in the black. You can't mismatch. It has to be match pairs. Exactly match pairs. ECC versus non-ECC. Error correcting code detects and corrects single bits. Non-ECC, no error correction. ECC needs support from CPU and motherboard. Ideal for servers, unnecessary from home PCs. Never mix ECC and non-ECC together. Now, the reason why it's not necessary from home PC is 2 things. 1, they are more expensive. ECC chips are more expensive. 2, if your workstation crashes because of a memory issue, just reboot it. Most of the time, that will fix it. For a server, you have like X number of people connected to it. You cannot be rebooting that server all the time. So you want to get the server ECC, error correcting code RAM chips, so you could correct it on the fly and you don't need to reboot. You don't need to put these on workstations. It doesn't make sense. You're only wasting money. Form factors for RAM chips, they're DIMM for desktops and SODIMMs for laptops. RDIMM and LRDIMM are servers buffered for stability at high capacity. Enable XMP on your Intels or XPO for AMD profiles in BIOS to reach rated speeds automatically. Unsupported boards may fail post, right, when they first start up. Troubleshooting. Random freezes, reset the RAM. Blue screen of death, run mtest 86. Boot issues, try 1 stick at a time. One time I bought new RAM sticks, and before you just put them in and you turn it on and the BIOS will automatically recognize it. This time it took me like a good minute of just sitting there with a black screen on before the RAM actually kind of like connected and the machine turned on. But yeah, it was weird. I thought I got bad RAM for a while from Dell, and then I waited like 1 minute and it just turned on. Just the first time. It doesn't happen after that. It was just like, I guess it needed to connect with the BIOS and update and notice that the motherboard that it changed, I guess. Story time. A workstation upgrade from an 8 gig to 16 gig with mixed brands. No dual channel, no performance gain. After installing a match to 8 gig kit rendering speed up 25%. Matching matters. So you got to match good. Memory takeaway, capacity equals multitasking, speed and latency is responsiveness, channels equals bandwidth, ECC is reliability. Next, CPU architecture and performance. The CPU is your system's brain, executing instructions, crunching numbers, and coordinating every process. Inside every processor is an ALU for math and logic, a CU directs operations, a register, tiny high-speed storage, and cache L1, 2, and 3 lightning-fast memory tiers. Cores are independent processing unit. Threads are virtual lanes created by simultaneous multi-threading or Intel's hyper-threading. More cores equals better multitasking. Higher gigahertz equals better single-thread speed. The CPU pipeline handles fetch, decode, execute, write back. Modern chips uses branch predictions and out-of-order execution to keep those pipelines full. Instruction sets, x86 or x64, complex instructions for desktop, ARM, RISC, simplify, power efficient, mobile and embedded, AVX, SSE, vector math for media, AI, and graphic acceleration. Cache hierarchical, L1 is 32 to 64 kilobits per core, fastest. L2, 256 kilobytes to 1 megabytes per core. L3 shares up to tens of megabytes. More cache reduces trips to RAM, boosting performance, sockets, and compatibility. Intel has the LAN grid array pins on the board. AMD has the pin grid array pins or pads on the CPU. Always match socket, chipsets, and BIOS versions. Chipsets defines the IOs, PCIe lanes, USB ports, overclocking. Check manufacturer CPU support listings before upgrading. Cooling solutions. Air coolers, reliable, affordable. AIO liquid coolers, great thermals, low noise. Custom loops, maximum cooling, high maintenance. Overclocking increases frequency for performance, but raises heat and voltage. Test with Prime 95, a Cinebench, and keep temps under 85 degrees Celsius. Undervolting, lower voltage for quieter, cooler systems. Common issues, no post. Check EPS, 8-pin, reset CPU, update BIOS. Thermal throttling, repaste, fix airflow. Incompatibility, were wrong socket or outdated firmware. A student installed a 13th gen Intel CPU in a 600 series board. Fan spun, no display. BIOS updated, fixed it. Firmware first, hardware second. Installation recap, lift the retention arm. This is for the CPU, right? When you're installing a CPU. Lift retention arm and align triangle marker. Place CPU gently. Lower the lock. Apply P-size paste. Mount cooler event. Boot, verify temps, and core counts. And the retention of the arm, there's something called there when you're lifting the arm. I forgot what that was called. If anybody remembers, email me. But when you're lifting the retention arm, it's not called retention arm. It's actually called something else. I can't think of it. But if anybody remembers, email me, professorjrod@gmail.com. Man, I can't think of it. All right. CPU takeaways, cores, multitask, cache, accelerates, architecture defines efficiency, and cooling systems sustain performance. Compatibility checks prevents headaches. All right. Now I'm going to give you 4 CompTIA style questions. I'm going to read them and then read them again, and I'll give you 5 seconds to answer them. All right, question 1. Which PSU standard introduced a 12-volt HPWR connector supporting up to 600 watts? A, ATX 2.4, B, ATX 3.0, C, EPS 12-volt, D, SFX. Here's the question again. Which PSU standard introduced the 12-volt HPWR connector supporting up to 600 watts? A, ATX 2.4, B, ATX 3.0, C, EPS 12 volt, or D, SFX? I'll give you 5 seconds to think about it. 5, 4, 3, 2, 1. All right, the answer is B, ATX adds 12 volt HPWR for high transistor GPUs. All right, next question. Which RAID level offers maximum speed but zero redundancy? A, RAID 0, B, RAID 1, C, RAID 5, D, RAID 6. Which RAID level offers maximum speed but zero redundancy? A, RAID 0, B, RAID 1, C, RAID 5, D, RAID 6. I'll give you 5 seconds to answer. 5, 4, 3, 2, 1. And the answer is A, RAID 0 strips data only. One failure equals total loss. All right, next question. A workstation needs speed and fault tolerance with 4 drives. Which RAID is best? A, RAID 1, B, RAID 5, C, RAID 6, D, RAID 10. I'll read it again. A workstation needs speed and fault tolerance with 4 drives. Which RAID is best? A, RAID 1, B, RAID 5, C, RAID 6, D, RAID 10. Now, this is actually a good question, because what you need to solve here is 2 things. You see the and is in the middle. So you need to solve need speed and fault tolerance. So whatever answer that you choose, it has to cure both issues that it's asking for, which is speed and fault tolerance. Now, out of these 4, which one does both speed and fault tolerance? And there's only one. D, RAID 10. RAID 10 describes stripping and mirroring for performance and protection. That's how you have to look at it. When they give you an and question, you have to look at it. Well, what are they? I got to meet whatever they're asking before the and after the and. Both conditions must be met. Or if there's more, at least 2, right, with the word and. But yeah. All right. Last question. After installing a new CPU, the PC powers on but no display. What's most likely the cause? A, bad RAM. B, insufficient PSU. C, outdated BIOS. D, faulty GPU. After installing a new CPU, the PC powers on but no display. What's the most likely cause? A, bad RAM. B, insufficient PSU. C, outdated BIOS. Or D, faulty GPU. Now, think about it. I'll give you 5 seconds. 5, 4, 3, 2, 1. All right. So the clue is new CPU. So, right? So it's not going to be the RAM, because it's not. And it's not going to be a faulty GPU. So you're left with insufficient PSU and outdated BIOS. And the answer is C, outdated BIOS. Newer CPUs often require a BIOS update to recognize the microcode. So, all right. Well, there you have it, guys. I hope you like this chapter on CPU and hard drives, specifically RAID. RAID is a big topic on the CompTIA exam. So I hope I taught you a lot. And until next time, keep tapping into technology. This has been a presentation of Little Cha Cha Productions, art by Sarah, music by Joe Kim. We're now part of the Pod Match Network. You can follow me at TikTok at Professor J Rod, that's JROD, or you can email me at ProfessorJRod, JROD, at gmail.com.